how are you all? I hope you all are doing well. We have started lecture series on CSIR NET SET Gate and other competitive exam too. So I already uploaded plenty of the videos for this previous year question papers. So which included linear algebra, real analysis, group theory, number theory, and so all the subject which is very much important for group theory, ring theory, and uh, uh, which is very much important for CSIR, NET, SET, GATE, and other competitive exam. So if you wanted to see this video, you may refer into my playlist. So in my today's video, I'm gonna explain to you all one of the question from real analysis. Okay, so we have to apply some basic concept in order to solve our solution. Okay, so now let's get start our today's question. First of all, I'm going to explain to you all question and then we'll move for the detailed understanding of solution. Okay, so question we have given f be a monotone non-decreasing real valued function O on R. Okay, on real what we have given f is a monotonic. Okay, so function f is a monotonic. Okay, which is a non-decreasing, that means which is a increasing. Okay, non-decreasing means increasing real valued function which is a real value, all value it's take on its domain codomain it takes from the real value. Okay, on R, then we have to figure it out which one of the option is correct. Okay, so first option it says that limit x tends to a, f of x exists at each point of a. Second option it says that uh, if a strictly less b, then limit x tends to a plus f of x lesser equal limit x tends to b minus f of x. Option number C it says that f is an unbounded function. Option number D says that the function g of x, which is equal to e to the power minus of f of x, is a bounded function. Okay, so we have four options and we have to figure it out which one of the option is correct within these four options. Okay, now let's get started today's solution. We'll go through the detailed understanding of each and every option because of question it is from the paper second, so which only the one option is correct, but all options are looking quite similar. Okay, so we cannot make the option directly correct, so try to discard the option by using some counter or by using some properties. So let's get start our today's solution. Option we have given limit x tends to a, f of x exists at each point of a. Okay, so that means whenever we apply every point from a, okay, limit from x tends to a, f of x exists. Okay, it gives exist a finite value for every point whenever we consider a. Okay, so we have given in a question f is a monotone non-decreasing real valued function on R. Okay, that means f is monotone. Okay, f is a monotone. Okay, f is monotonic given a non-decreasing real valued function on R. Okay, next condition, non-decreasing real valued function, real valued function. Okay, on R given. Okay, so these two conditions are given. We have to keep in mind these two conditions. Okay, so we have to take these conditions front of our face and then we have to uh, take some counter example. Okay, that we can make the option wrong or we can make the option correct. Okay, so we want the function is a monotonic. Okay, so we want the function is monotonic, and second condition which is the non-decreasing. Okay, so we cannot guarantee about it is increasing, but we want it is non-decreasing. Okay, so we cannot say about increasing. So we know that there is a function which is a greatest integer function. Okay, so whenever you're going to plot the graph on a greatest integer function, you will get the stepwise graph. Okay, sometimes increasing, sometimes decreasing, something like this. Okay, now let me explain through this graph of a sin x. Okay, so any graph you may consider. Okay, any graph, whatever you want. Okay, any graph if you want you may consider. Okay, so for your understanding, just for understanding, I'm going to explain here how the monotonic non-decreasing or increasing functions look like. Okay, so I taken as a greatest integer function. Okay, so for example, I consider here sin x. Okay, so how the graph of a sin x for greatest integer function it look like. Okay, so which we may consider as a modulus of greatest integer function of a sin x. Okay, like this. So, what is the graph of sin x? It is says that okay, sin 0 is always 0, sin pi by 2 it goes to 1, sin pi it goes to 0, 3 pi by 2 minus 1, and so on. Okay, like this graph is coming for sin x. Okay, so it is similarly for here other side. Okay, so this is the graph of a sin x. So greatest integer function of a sin x means, so we want the graph which is a piecewise continuous. It is the definition for greatest integers function. So the graph of a sin x, okay, greatest integer function of a sin x, sin x it is look like. Okay, so we want the graph of a greatest integer function of a sin x. So this is the one interval, another interval again here. So these are the interval which I plotted here for better understanding. Okay, so because 0 it is a pi by 2, 3 pi by 2, again 2 pi. Okay, so we have to go for the periodicity here, so you will get the graph here. Okay, now here again we got this one. So greatest integer function of a sin x, it says that we get the step from this value to this value, we got the first step. From second value, from this here to here we got the second step. Then third step it is here. Okay, then fourth step it is here. Okay, fifth step it is here. So these are the steps, these are not connected graph. Okay, so greatest integer function of sin x, it is having not connected graph. Okay, so this is the first part, again it is second over here, third here, fourth here. Okay, so this way the greatest integer function of a sin x can be drawn. Okay, so I hope you all have understood how can we draw the graph of a greatest integer function of a sin x. Okay, now as we observe, the sin x, greatest integer for function sin x, is a monotonic. Okay, okay, it is having monotonic property. It is a non-decreasing, so you may see that sometimes it is increasing, sometimes it is decreasing. That means if it is increasing, that means it is a non-decreasing. Okay, so it is sometimes it is going to decrease here. Okay, so it is a non-decreasing, sometimes it is increasing, sometimes it is decreasing, but there are some interval available here. So for that particular interval, that sin x is a non-decreasing. Okay, so that means I got the value of a greatest integer function sin x, which is a non-decreasing and monotonic. Okay, just need to understand only how we can define the greatest integer function. Or you may take any graph or y which is equal to greatest integer function of x. So we will get the graph like y which is equal to x here, like y which is equal to x, and there we will get the great step of the functions. That means it is, we get the some interval over here, some interval over here, some interval over here. Function is discontinuous for every interval. That means greatest integer function is having some kind of a discontinuity. So we learn already like a jump kind of discontinuity. Okay, so greatest integer function is having jump kind of discontinuity. So it's like a first jump here, second here, third here. So this is a jump kind of a discontinuity. Okay, so why am I explaining this discontinuity? Because it's our option, it says that limit exists for f of x, and when limit does not exist, limit x tends to positive value which not equal to limit x tends to negative value. So whenever such a condition hold, then we say that our limit does not exist. That means positive value and negative value, it gives a different answers. So that means function is not continuous, that means function is a discontinuous, and if function is a discontinuous, it has some kind of a discontinuity. But I found here it is having some kind of a discontinuity, like a jump discontinuity. Okay, so greatest integer function always having jump kind of a discontinuity, like removable discontinuity. Okay, so greatest integer function, always remember greatest integer function, it is always having irremovable discontinuity or a jump kind of a discontinuity. Okay, that means the function is a discontinuous. If a function is a discontinuous having irremovable discontinuity, that means definition of irremovable discontinuity, it says that limit as x tends to a plus of f of x not equal to limit as x tends to a minus of f of x. Okay, so these values are never equal. Okay, so positive and negative value are never equal, and if such a condition happen, the by the definition of a limit, we say that limit as x tends to a f of x does not exist. Okay, which is does not exist. So it is very much easier question. So what I have done in our option, so in our option we have given limit x tends to a exist for each point of x, okay, and f is monotonic and non-decreasing given. So using this I consider greatest integer function of a sin x here, okay. So for your understanding, so I plot the graph, it is having some kind of discontinuity, and if function is a discontinuous, then we say that limit does not exist, okay. So we need a function continuous to show the limit exists, okay. So if I got the some kind of discontinuity, okay, it's a irremovable discontinuity in our function greatest integer function of x, okay. So it gives positive negative value, it gives us a different values, okay. So if it is function is having irremovable discontinuity, that means this condition hold, okay. So this is the definition for irremovable discontinuity, okay. And function is having irremovable discontinuity, that means positive limit negative value not equal, and by the definition of limit we say that limit x tends to a f of x does not exist, okay. So this is our first option. It is quite a bit lengthy, but I hope you all have understood, nothing is difficult here, okay. Now let's get start our second option. Now next option is given C, f is an unbounded function, okay. So B option I kept it for later solution, okay, because it is quite confusing that we cannot show that option B is correct, okay. So we have to find out some counter for B. So for C, it is given C is an unbounded function, okay. Now we have to consider, okay, we have to consider over here, so C option f is an unbounded function, so we have to consider over here such a function that is a bounded function, okay, but it is having the property that function is monotonic as well as non-decreasing function, okay. So we have to consider such a function over here that can be satisfies our solution, okay. Option C. So here f is an unbounded function. Now let's consider f is a bounded function, okay. So we have to make it wrong, that's why we have to consider f is a bounded function, okay. F is a bounded function, then show that f is monotonic as well as non-decreasing and real valued function, okay. So bounded function, we know that we can take directly the constant function, okay. Constant function is the best example here to consider the function is a bounded, okay. So if I consider f of x which is equal to any constant value you consider, I consider 1, okay, only single constant one. So f of x is a 1 I consider over here, okay. And we know that constant function always monotonic decreasing as well as monotonic increasing, okay. So always remember constant function always monotonic increasing and decreasing, okay. So constant function always monotonic increasing and decreasing, okay. But in our option we have given f is monotonic, okay. So f is monotonic here, it is always monotonic, constant function always monotonic. Non-decreasing means f is increasing, so f of x is a increasing also, that means non-decreasing, okay. So f is increasing, that means non-decreasing. So our f of x, which is a constant function, which is a bounded function, I consider here, which is a constant, which is a monotonic as well as monotonic increasing, monotonic decreasing, okay. That means it is a non-decreasing too, okay. So function I consider here which is a constant but which is a bounded function, okay. If I consider bounded function, this property violate, okay. So option number C, I can say that which is wrong over here, okay. They have given unbounded function, okay. So it is hold for unbounded function too, but I got the counter example that says that our function which is bounded, okay. So f of x which is bounded over here, so f of x is bounded, that means our option number C is wrong, okay. So I got this property true for f of x which is equal to bounded function, okay. So option number C which is wrong. Now let's move for the option number D. Now in our option D, so we have to show g of x which is equal to e raised to minus of f of x is a bounded function, okay. So for to show this one, we have to consider f of x which is such that g of x is not bounded, okay. Try to go for the opposite direction of our question option, okay. So if I consider f of x which is equal to x, okay, f of x is equal to x I consider over here, okay, which satisfy the given condition, okay. So f is monotonic, okay, f is a monotonic, okay, f is a monotonic. Now next condition, it shows that f of x is equal to x, okay, which is a non-decreasing. Yes, it is true. Okay, f is a non-monotonic as well as non-decreasing. Okay, so f of x I consider x. Okay, now put x is equal to in our function g of x and show that it is bounded or not bounded. Okay, so if I consider g of x which is equal to e to the power minus of f of x. F of x is x. Okay, so e to the power minus x. Okay, and we always know that f of x g of x is equal to e to the power minus x. Okay, and we always know that e raised to minus x which is a non-bounded. Okay, which is a non-bounded function, which is a unbounded. Okay, not bounded means the function which do not have upper bound and as well as lower bound. We cannot say some certain fixed value is the upper bound for our f of x and a lower bound for f of x. Okay, that's why we say that g of x is equal to e to the power minus x, which do not have upper bound and lower bound, so it is not bounded, obviously unbounded. Okay, and now left over option b we have here. Okay, so we'll go through the option number b. And option B, if a strictly less b, then limit x tends to a plus f of x lesser equal limit x tends to b minus g of x. Okay, so if all the options are wrong, then option obviously B is a true. Okay, so you may take any other counter example that the value for a need to be bigger and b need to be a smaller. Okay, so this will be hold. We want the function. Okay, we want the function where function is monotonic as well as non-decreasing. Okay, so already we consider some constant function. So if I consider limit x tends to a plus 1 lesser equal to any value, you may consider limit to the constant and any value to the constant g of x, we'll get the one which is equal to 1. So this condition hold for constant function also. Okay, which is monotonic as well as monotonic increasing and decreasing. This is hold for other functions too. Okay, so you may take any other counter example, this will be hold. Okay, so this is the option number B, which is a true over here. So I hope you all have understood my complete solution. So for your better understanding, you may refer my solution. Here it is, complete solution, which gives option B. Okay, so I didn't given here any counter for option B because it is obvious property, or you may take any counter which will be true. Okay, for option number C. Okay, this is the certain options. Okay, they are always true. So I hope you all have understood my today's complete solution. Even after, if you have any doubt, difficulty, let me know in comment section. So thank you everyone. Thank you for my today's lecture.